Welcome to this module on highly purified water storage and distribution system. This training will take 30 minutes to complete. Here are some tips to get started. Click on each topic below to learn more about how you can interact with the course. General overview. This GEMS guideline describes the minimum expectations for ensuring that the highly purified water storage and distribution system for TIVA manufacturing facilities are appropriately considered. Purpose. This guideline defines the approach to design of a purified water or highly purified water storage and distribution system to suit TIVA manufacturing standards. It will also be a guide on primary GMP requirements with respect to basic operational, sampling, sanitization, equipment, and components. In this module, we will learn about the guidelines that apply to the design of storage tank, distribution piping, associated system components, point of use, and operating parameters. These guidelines must be used as the basis for all new systems or for the addition and modifications of existing systems. Design expectations and recommendations in this module are based on accepted industry practices. The following internal and external documents were consulted in the preparation of this guideline. Click on each reference tab to view them. The purified water storage and distribution system is considered as a critical system. Hence, a well-defined user requirements specification and a functional design specification document must be prepared. The URS document must specify intended applications, safety and GMP requirements for the system, water, chemical, and microbiological requirements, list of main components, preliminary sizing, functional requirements, materials of construction, equipment surface finish, biological control concept, control interlocks, alarms, and warnings, documentation required, validation requirements, performance qualification monitoring parameters, and consumer flow rates and temperatures. The system must be sized, controlled, and regulated to ensure a dynamic balance between the supply and demand of appropriate quality of water as per governing regulators such as US FDA, MHRA, European Pharmacopoeia, and Japanese Pharmacopoeia, or any other as applicable. Such supply should be uninterrupted to meet the point of use requirement in terms of flow rate, volume, pressure, and temperature. Here are the specifications for purified water and highly purified water. The PW or HPW system is considered extremely critical because it is used for intermediate or final rinse of production vessels and equipment depending on the SOP. It is also used as the feed to WFI and pure steam generation. Hence, it should be carefully designed, built, and installed in alignment with regulatory requirement. Let us understand the key components and their purpose of a typical PW storage and distribution system. Highly purified or purified water generated is fed to a storage tank, which is equipped with various instruments and components such as temperature transmitter to measure the temperature of water during sanitization, continuous level transmitter to indicate the level of water in the tank and to control the production of PW, Alternately, load cells or static pressure sensors can also be used for this purpose. Spray ball to ensure the unsubmerged surface of the tank is always sprayed with water to resist formation of biofilm. Vent filter is a very important component. Its purpose is twofold. One is to maintain near ambient pressure in the tank while ensuring its sterility. The other is to filter out viruses and microorganisms from the air as it flows into or out of the tank with its changing water levels. Sight glass is used to allow the operator to view what is happening inside the tank. Manhole is necessary for maintenance and internal cleaning. PW from the tank is supplied to the production rooms using a sanitary pump. This pump is designed to deliver water at each point of use and maintain the distribution loop in positive pressure of minimum 1 bar at any given time. A variable frequency drive should be used to regulate the impeller speed to optimize on the energy consumption while maintaining the pressure. Dump valve is installed in the distribution loop to immediately stop supply to production and dump the water in a situation of quality failure. The dump valve receives command from the conductivity transmitter. Point-of-use valves should be zero dead leg or T-pattern block valve. These valves can be manual or automatic. However, the valves connected to the process equipment or vessels should be automatic with a built-in sampling valve. A cluster of instruments are installed in the return line of the distribution loop, such as conductivity transmitter to ensure the conductivity of PW is within the acceptable limits. Pressure transmitter to ensure the distribution loop to be always in positive pressure. Flow transmitter is used to control the return line velocity, ensuring turbulent flow in the pipeline to resist microbiological growth. Temperature transmitter to control the function of the return line heat exchanger responsible to maintain the overall system temperature within set limit as per sanitization SOP. TOC meter to analyze the total organic carbon in water. Inline sanitary design heat exchanger is used for sanitization of the loop, including the tank, as illustrated. The distribution loop should circulate water continuously 24/7 to keep water available for production at any given time and to resist microbiological growth. To learn about system capacity, click on each tab. The overall capacity of a purified water storage and distribution system consists of 3 components. They are generation capacity, storage capacity, and consumer demand rate. The storage tank should be sized to handle the sustained daily demand while being filled from the generation system, without dropping below typically 30% capacity or the pump NPSH, whichever is lower. The peak demand, sustained demand, and minimum tank level requirement should be used to optimize the storage volume in relation to the PW production flow rate. The distribution system should be large enough to provide the maximum diversified load demand at the required flow rate and a minimum required pressure at any point of use. Selecting pipe materials, methods, and system components. All materials and components used in the PW distribution system must be carefully selected to ensure compatibility with working temperatures, working pressures, cleaning, passivation, and sanitization chemicals, and regulatory acceptance. For piping and fitting, the following materials of construction should be selected: Type 316L or 316LTI stainless steel for all components that are welded. Type 316 stainless steel for components that are not welded. For example, pumps. SS 316L and better. 316L electropolished should be preferred where available. Internal surface finish for equipment, piping, and fittings must be less than 0.6 micrometers RA and electropolished. Pipe gaskets must be EPDM core with a Teflon coating or other materials meeting USP Class 6 requirements and the operational conditions. Typical system components consist of purified water storage tank with vent system, purified water distribution pump, recirculated distribution system supplying the points of use with the return of purified water to the storage tank, heat exchanger to heat up and maintain sanitization temperature of the recirculated purified water, and for point of use as applicable. Required instrumentation and controls sufficient for the proper operation and control of the system. Click on each numbered button to learn about considerations that need to be taken while designing the purified water storage tank. Purified water storage tank should be vertical. Horizontal tank should be opted only where space is a constraint. It should have spray ball to ensure the unsubmerged surface of the tank is always sprayed with water to resist formation of biofilm and for cleaning and passivation process as and when required. A manhole of minimum 450 millimeters or a size as per local standards must be considered. Tank should be completely drainable through the bottom outlet and have minimum dead legs in attached instrumentation and piping. Design and fabrication must comply with the latest ASME, BPE, or PED for process vehicles for 3-bar gauge pressure and full vacuum to support pressurized operation or steam sanitization. Next, we look at purified water distribution pump. Purified water specification. The pump must be sanitary open impeller type with a single mechanical seal of SC on SC and a bottom casing drain. To learn about the functions that a purified water distribution pump serves, click on each numbered button to learn. It must be sized to supply purified water to all user points at required pressure and flow rate as per the production needs. The pump will circulate purified water through the distribution system 24/7 while maintaining a continuous positive pressure of minimum 1 bar. If dual pumps are installed to provide redundancy, they must operate in such a manner that both pumps have continuous flow through them. Pumps may be fixed speed, but variable speed pumps are recommended for startup and for better reaction to the widely varying flow rates usually encountered in purified water distribution systems. Variable speed pumps may be controlled by flow rate or pressure as monitored at the end of the purified water distribution loop. Valves in purified water contact must be sanitary diaphragm seal type with a weep hole in bonnet. To learn about heat exchangers, click on each numbered button. Heat exchangers are used to heat or cool the purified water to the desired temperature. Heat exchangers for cooling can utilize cooling tower water, chilled water, or water glycol combination, while plant steam should be used for heating. The preferred type of heat exchanger is a double tube sheet. All heat exchangers should be built in SS316 or higher alloy for sanitary design with maximum drain ability on both the process and utility side. All heat exchangers should be provided with a sealant coating prior to installation. Appropriate thickness and MOC of a non-chloride and non-asbestos insulation must be provided with a SS304 or 304L stainless steel sheet cladding. Instruments should be installed with provisions for maintenance, so calibrations and repairs can be completed with minimum downtime of the purified water loops. Click on each numbered button to learn more about instrumentations. Redundancy is not required for any instrumentation. One of the following instruments should be selected to measure water level in the purified water, highly purified water storage tank: load cells, guided radar, or balanced differential pressure. Instrumentation for main distribution loop: flow measurement, installed at the end of the loop in return line to the tank. Pressure monitoring, at pump outlet and end of loop. Temperature measurement, end of loop. Conductivity, end of loop. And TOC, end of loop. TOC. The side stream must not be returned to the process water system and must be discharged to drain. Monitoring of multiple points or process streams should be accomplished with a single TOC analyzer equipped with an automated sample sequencer rather than multiple analyzers. Subloop instrumentation. Subloops are recommended to have similar instrumentation as the parent system and additional process-specific if need be. Here are the parameters for alarms and the required actions that need to be taken. Next, we look at vent filter. The vent filtration system is for the exclusion of particulate and airborne microbial contamination. It should be heated to a temperature that is at least 10 degrees centigrade above the purified water temperature to prevent possible condensation of vapor inside the vent filter. The heat tracing is only needed when the water is hot. If the system is operating at ambient temperatures, then there is no need to operate the vent heater. Vent filter temperature indication should be monitored automatically. Drag each numbered circle and drop it onto the blank circle on the left to learn about loop types. There can be any number of pipe distribution line designs, usually comprised of one or more loops or subloops. Non-recirculated systems must not be used. The single continuous loop can be used when all use points can use the purified water at the same temperature. Subloops can be used when there are different users that can be grouped together according to temperature or based on their position in the plant. The subloops can be of diameter smaller than the main loop. Separate main loops can be used when the users are spread out over a large area or with great differential of heights. Differences in consumer supply pressures can also dictate the separation of loops. Main loop pressure drop can be reduced significantly if needed by using a system of subloops or separation into two loops. The loop pressures must be designed by the following guidelines. Minimum 1 bar G pressure on the return spray ball in the tank for proper operation. Minimum of 1 bar G pressure on any point of use in the loop. Pump discharge pressure typically should not exceed 9 bar G, considering the possibility of the presence of any inline ultraviolet sterilizer in the loop. If it is not possible to meet all the above guidelines, the loop diameter should be adjusted or the loop configuration should be changed. For example, separating a single loop into two separate loops. To learn about pipelines, click on the center button. Purified water branch piping should be sized according to the flow and pressure required for the point of use it serves. The materials and installation should meet the latest ASME BPE standards for high purity piping, including the use of sanitary clamp connections, material traceability, welding techniques, and documentation. Tubing should comply to ASTM A270 S2 standards. Connections in the piping system should be welded wherever possible, including valves. When welding is not possible or practical, sanitary clamp fittings should be used with bolted clamps for increased safety. In order to resist microbiological growth and biofilm formation, the distribution piping should be free of dead legs as far as possible. Appropriate slopes in the piping must be provided to facilitate drainability. The flow in the pipeline should be maintained turbulent, and zero dead leg valves should be used for all point of use and sampling. Dead legs should be designed for a length of 2 pipe diameters or less. If not, then microbial growth must be controlled, such as periodic flushing for a specified sanitizing duration. For legacy systems, dead legs can be a maximum length of 3 pipe diameters for an ambient system and 4 pipe diameters for a hot system. The distribution system should be sized to provide the maximum diversified demand load at the required flow rate and minimum required pressure, while maintaining a specified minimum return flow rate to the storage tank. Branch connections to the users should be sized for a pressure drop of 0.5 bar per 100 meters or less. The minimum available pressure and flow rate at each point of use drop should meet the user's requirements.